what we're going to be going over here is linear regression, and we're going to be looking at ANOVA here. Really, that's the analysis of variance. And we're going to be looking at two different tests here, the R-squared and the F-test. And we'll be concentrating on this F-test, but we're going to look at how this R-squared and the F-test here are related. Okay, so what I've done here, I've got 12 different data points here that we did a regression analysis on. So along our x-axis, that is our independent variable here, refer to it as x. And along our y-axis, that's our dependent variable here, y. So we've had these 12 different data points that I looked at, these x, y data points here. And we want to find out here through this variance analysis, we want to know if the variation of y here is explained by the variation in x. So we want to determine whether y here is related to y, our dependent variable here, is related to x, our independent variable here. Okay, so what you're going to really do here, and we'll look at it just in terms of what the software package would have done here, and I've done it, we'll look at it in terms of Excel here because they've got a basic software package for doing this analysis here. Okay, so what I would have done here, for this 12 different data points, we'd have come up with a y mean average here. And it's shown here along this horizontal blue line here. And then the regression would have been done against those 12 different data points, and we would have plotted a line here. And that's really the mean value here of, in this case, we got a regression line here which only has one coefficient here. So y, the dependent variable here, equals m, the slope of the line, times whatever x value you put into it, plus b here, and b is the y-intercept here. When x equals 0, we have a b value here. So this regression line was plotted here by the computer here doing that software. So what we're going to do here, based on this mean value of our regression line here and our mean average value for our y datas here, we're going to have to determine the totals. We're looking at the sums of squares here. So really we've got three different values that we have to look at here. We call it the total sums of squares, and that's really the difference between this mean average value here and whatever a actual y value you have. So you would have done that for those 12 different data points here, and that you can see the difference here. This total sums of squares I'm showing here in blue here. So that's coming off your mean average and your actual data points. All right, and then we've got the residual sums of squares, and they refer that as the not explained portion here of the total sums of squares. And the residual is just coming off the actual data point here again for y, and then what we would have predicted here based on our model here, the predicted y value here. So those values, again, we would have squared those and summed them up for those 12 different data points. And then the only other value we have to be concerned with is ESS, or that's the explained sums of squares here. And that's really the difference between your y mean average value here and whatever the predicted value would have been by your model or your line here. So those are the three values that we're going to have to deal with here. Total sums of squares here, the residual sums of squares shown in the green here, and then the residual sums of squares plus our explained sums of squares, ESS here, those equal our total sums of squares just as shown here. Again, so total sums of squares here equals our explained sums of squares amount and plus the RSS, or the not explained sums of squares. So just look, so we're looking for the variation in y that's explained by the variation here in x. That's what we're doing here. So just our general equation here for summing, we would have had total sums of squares, y actual value less the y mean value. That difference squared, you sum up from 1 to n data points, and we had 12 in this case. And then the residual sums of squares, again, y, the actual data point, difference between a y actual data point and the predicted data point off that regression line, that difference squared. And you sum those squares here from 1 to n data points. In this case, we had 12. And then lastly, our explained sums of squares, ESS here. Again, this is coming off the y mean value here, less the predicted value here based on our regression line. That difference squared, again, sum them. Okay, so that's what we're dealing with here. Okay, so now let's go and let's look at our F-test here. And we'll just look at it in terms of an Excel output here. So really what we're going to be we're going to look in this R-squared test, we're going to be looking at that, how it's related to our F-test here. So let's just look at our F-test first here. So with our Excel output, we're going to have this ANOVA line here. And this is remember those three different values that or regressions that we're looking at here. The ESS, that was the explained sum of squares, that's the regression amount here. And then the residual RSS, those were the residual sums of squares. And then we have our total TSS here, total sums of squares. So that's what you've been given here. And you'd had some degrees of freedom. And we're going to go and look at how we calculate those degrees of freedom in general here. And then you're going to have your sums of squares, your mean sums of squares, and then you're going to have this F statistic here that we're going to look at. So what we have to do here with this test, we have to determine if our F test meets a critical value here. And we're going to base it on a 5% or a 95% confidence that these variation in Y is going to be explained by the variation here in X. So the first thing we have to do is go into an Excel here and just see how this is set up our critical value here. And I'm showing this F, this is the typical F distribution that you'd be using for the F test here. Okay, so back to our Excel, we just determine that critical number here, F.INV.right tail here, RT, and then we would put in the percent that we're looking at. In this case, it's a 5% factor that we're looking at, 95% confidence here. And then we got two different degrees of freedom that we'll go through. First degree here would be our explained sum of squares here, the degrees of freedom for that. In this case, it's 1. And then for the next one would be the residual sums of squares, and that here is 10. Okay, so put those numbers in here, hit your enter, and you're going to get a critical value here, 4.964603 here. Okay, so that's what we're going to use for our checking whether or not these variables are related here. So we put in, I'll go to our curve here, just looking at our curve. We have our critical value here at 5%, we calculate 4.96. Now, with our F statistic here that Excel we come up with 10.89573 here. Okay, so putting that on our graph here, you can see here this 10 is greater than our critical amount here. So what we're saying is here, yes, we meet our critical amount here. Had it been less than, had our F been 3 or 2 or 3 or less than anything less than 4.96, there wouldn't have been a relationship, wouldn't be no here. So, but it's met our critical criteria here. We're sitting at 10.89, which is greater than a 4.96 here. So that's all it's telling us is yes, there is that relationship here. And the other thing is we'd only be, our significance of F's, we'd only be wrong 0.008% here. So we're pretty confident that there is a relationship based on our F test here. And then the other thing we'll look at, just to mention it here, the R-squared test, it was at 0.52, which is 52%. And that's sort of a moderate amount here. Generally, they look at 30% or greater as being there is a relationship in that. So we're sort of sitting at a moderate amount here. Okay, so back to our ANOVA, just to understand what that is. And we're going to really be going through, looking at it here, this ANOVA, our degrees of freedom. Degrees of freedom I'm showing up here, and just related to what we're talking, we got some different numbers here, sums of squares here, and then we got our mean squares here, and then I got our F test here. So for our regressor, our ESS, the degrees of freedom, this is what we're going to go through as K, and we'll look at that here. Just look at what they are here for the time, just referred to as K, and that's going to be the number of coefficients we have here in our equation. And we only have one in this case here. So for our problem, we've got only one coefficient here. That was that X variable here, the coefficient for that X variable here. So our sums of squares is for our regression here, ESS, is really our total sums of squares less our residual sums of squares. If we went back to our diagram and looked at it, we'd see that. So that's our sums of squares here, based on it, just taking our total sums of squares that's shown here, 607,000 here, less 292,000, or 290,000, you're getting 31,600 something here. Okay, so then for our regressor, our mean square is just taking our regressor, or ESS, our sums of squares here, and divide it by the degrees of freedom, which we'll be looking at, and that's going to become our numerator here in our F test. And then for our denominator here in our F test, that's the residual, looking at our residual sums of squares. Now the degrees of freedom for that is N minus k plus 1 here. That k plus 1, and subtract that from n, that's the number of observation. That's going to be the residual degrees of freedom here. And if we've gone up to our quantity here, we have 10 here. And remember, we had 12 different data points here. So we have 12 different data points, 12 here. And then we only have a factor here of only 1 for our k value here, for our coefficient here. So 1 plus that 1, plus 1 here, 1 plus 1, 2, and subtract it from 12, and you're going to get your number 10 here. Okay, so your sums of squares for your residual, you would have had that. And then the mean square is just taking the residual sums of squares and divided by the degrees of freedom here. So for our f-test, we've got the amount here would be our explained sums of squares, ESS here, the mean square value of that divided by the residuals sums of squares, the squares for that here. So that's going to give you your f-test here. So had we gone up here, it would have been what? It would have been our mean square here for our regression for our ESS, 31,000, oh, what is that? 316,000 divided by 29,082 here. The mean square of the regressor ESS divided by the residual amount here. And that's going to give you your F statistic that you have to be looking at. That in this case it was 10.89 here. Okay, so that's our ANOVA. And then just one other point here, that total sums of TSS here, the degrees of freedom with that would be n minus 1. And n is the number of different data points we looked at here. In this case we had 12 different data points. Minus 1 gives us a total here of degrees of freedom of 11. So sums of squares for TSS here. Okay, so that's for just understanding our ANOVA here. Now let's just look at calculating these degrees of freedom, or determining our degrees of freedom, because this is critical here when you're doing this f-test. You have to know what those degrees of freedom are here for both the numerator up here and for ESS here, and your denominator for your RSS here. In order to either interpret that, get that F value off some F table, or putting it into some equation like or function like for Excel, you have to know what your degrees of freedom are. So let's just go and try to understand that here. So that we talked about that k value shown in green here. That's the number of coefficients. And in your equation here, in our case, we just had that one coefficient here, y, or predicted y equals m, the slope of our regression line, times rx, that is our independent variable, plus b here. So we only have one coefficient in this case. But k really, if you look at it in this terms here, say for example you have a regression here where you got x1, x2, and x3. Those are three different independent variables. Well, you'd have a coefficient factor for each one of those. So in that case, your k, or your number of coefficients, would be what? 1, 2, and 3. So you'd be using in your formulas up here, or your k value up here, you'd be using that as 3 here. And then n here, what we have used in our degrees of freedom here, that's really just the number of observations we have. And in this case, if we had this regression here, would be how many predicted values you have here for y, number what you put in here for your regression. Okay, so that's really definition here for how you get your k value here and your n value here. So let's just look at it in these terms. Remember, we said our total sums of squares here equals our estimated sums of squares plus our residual sums of squares here. So really this equation is important if you're trying to determine your degrees of freedom here. So if you know any value for two of these, then you can solve for the other one here. So for our total sums of squares, that would have been n, number of data points here, minus 1. And then for our explained sums of squares, that's that k value here. Those are the number of coefficients for each of the independent variables that we're regressing against. And then the RS here, that's really taking n, the number of data points, and then you subtract from it whatever k value you have here, and you add 1 to that. This k plus 1 here, subtract that here from n. And that's for your residual sums of squares. Now, it's important here because understand this ESS here, that K value, that's going to go into the numerator. So if you're using an F test, they're going to, and a table and something, you're going to have to look at the numerator value and you have to compare it to the denominator value. And the RSS here is in the denominator because that's what, when you look at this ratio here that you're really looking at, that's how it works out here. Okay, so TSS, n minus 1 here, degrees of freedom, number of data points. ESS, just K, the number of coefficients. And then RSS, n minus the quantity here, K coefficients plus 1 here. Okay, and just working this equation out here, looking at your degrees of freedoms here, so n plus 1 here equals K plus n, and then you would just break these apart here, minus K plus 1 here. So you can see your K's cancel out here, minus K plus K. So you just end up with the n minus 1 equals n minus 1 here. Just solving for your degrees of freedom. So worked it out here. So for our example here, our TSS, we had 12 data points here. Minus 1 would be 11. And then our ESS, our K value is just 1 here. And then our RSS, we have 12 data points, minus K of 1 plus 1. So we end up with 10 here. And plus 1 for our ESS here does equal 11 here for our TSS here. Okay, so just understanding the relationship. I guess the big thing here is the computer programs all do it for you, but you really have to know, look at how you calculate these. You know your K and your N numbers. Just remember, N here is the number of observations, and K is the number of coefficients or the independent variables that you're regressing against here. And then the other thing, just remember here, looking at our little deal here, our ESS, we're going to go and look at it in terms of the R squared here, but that sits in the numerator here when you're checking it out, either putting it in a formula or on the table. Just remember that's the numerator here, the ESS, the K value, and then the denominator value is your RSS here, N minus the quantity of K plus 1 here. Okay, so next we'll go and we'll look at this R squared and see how it's related to the F statistic. Okay, now let's look at our R squared value here, that 52% or 0.5214 here, and compare it to the F statistic here of 10.89 here, and see how the two are related, your F statistic here versus your R squared here. Okay, so let's go up here and let's look at our relationship here. So for R squared, by definition, is 1 less the fraction here of the residual sums of squares divided by the total sums of squares. So residual here is that green value, our arrow here in green for our residual sums of squares, and then our total sums of squares is shown over here. So you've got that fraction here, or that ratio here subtracted from 1, and that really equals your explained sums of squares versus your total sums of squares here. Explained sums of squares shown in gold here divided by your total sums of squares here. Okay, so that's our squared value that we have here. So you take that R squared value here and you divide it by the K, the degrees of freedom for the numerator, the ESS here. Those are those K coefficients. And then you take that quantity here and you divide it by 1 minus R squared here, and divide that by the denominator degrees of freedom here, your RSS, or residual sums of squares, and that's your N minus K. N is the number of observations, K is your coefficient here, plus 1, that quantity. So you divide those denominator degrees of freedom here into 1 minus your R squared value here. And that you divide into R squared divided by K here, and that's your F statistic here. Okay, so for our F statistic applied to our problem that we have here, our squared value was 0.521 here, and then we had 1 degree of freedom here for our K coefficients here, and then that quantity divided by the 1 minus our R squared. So if you take 1 minus R squared, you're going to get 0.478 here, and you divide that by the degrees of freedom here for your RSS, your denominator, and we had 12 data points less 1 K coefficient degree of freedom plus another 1 here. That gives us 10 here. You divide that into 0.478, and then you take that total quantity and divide it into your R squared here, 5.21, divided by 1 here. And you're going to come up with an F statistic here of 10.89 here. And that's exactly what our Excel program or our statistical regression shows here, 10.89 here. And remember, this F statistic, that's really taking your explained sum of squares, the mean squared value divided by your residual sum of squares, your mean squared values here. Okay, so that's just how the relationship here between that R squared value here and your F statistic here. So they're tied in. In this case, our F statistic based on our critical value here, 0.496 here, versus what we actually have here, 10.89. Yes, we do have a relationship here where our X independent variable is explaining our Y dependent variable. And same shown over here for your R squared value here. We have 52% correlation here. And really they're saying anything over 30% gives you some correlation here. But nonetheless, we looked at your R squared here and how it's tied into the F statistic, your F test here, based on that the F test is based on F distribution here. Okay, so that'll summarize our discussion here.